to be here. But the positive side of this is that that'll be less material that you're going to have to know, right? And the test is going to be on Monday. We're going to cover some new material today. Stop me at about 1:40, maybe 2 o'clock tops, and then we'll talk about the test. And my plan is to just kind of give you, like almost like we did last time, where I give you sample problems, but I just don't have them all written out or typed up for you. So I'll just go around the room and I'll put a bunch of problems on the board, and then I'll work through them, and then you can kind of work through them on your own also. And yes?
Just a quick question. So far we've done just polynomials for the test?
And rational functions. That's right. Yep, so there's really only 2 topics. I forgot to bring, oh no, I did bring them. I have all of your stuff you've turned in, with the exception of what you brought last class. So I'm going to hand this out, pass this around the room, go through the entire stack, and pull your stuff out. And the grades have been updated on Canvas. All right? So this will come around. All right, so today we are going to talk about exponential functions. So we've dealt with, so far, we've done linear functions, we've done quadratic, we've done polynomial, we've done rational functions, right? We should be able to graph all of these. And we also learned that polynomials, quadratics, and linear functions are all part of the same family of functions. A line is a polynomial, a quadratic is a polynomial, but you can have higher orders, you can have higher degrees. And then the rational functions, they're their own, entity, but they involve polynomials. It's a ratio of 2 polynomials. And we saw with the graphs, they had these weird things and asymptotes and all this weird behavior, right? So we are now introducing another type of function called an exponential function, and this will be the last, second to last type of function that we'll talk about. So what I'd like to do is kind of get this whole idea motivated with a sacrificial piece of paper. Who's got my sacrificial piece of paper today? Thank you, Mom. You know what? I'll take them both. I'll sacrifice them both. All right, so I want you to help me out here. What I'm going to do is I'm going to take this piece of paper, all right, and I'm going to start making folds in the paper. So if I do not fold this piece of paper right now, right, if I do not fold it, how many rectangles do you see? 1. Okay, so this is an example I'm doing of folding paper. And I'm going to make kind of like a T-table. It's going to be the number of folds here, and over here the number of rectangles that you see. All right? So we said 0 folds, 1 rectangle. If I fold it 1 time and open it back up, how many rectangles do you see? And let's count the crease as being, where it's separated. I could come in here and draw a line down the middle now or something, right? So how many do you see now? 2, right? So I fold it 1 time, I see 2 rectangles. So now I'm going to fold it twice. So I fold it once, and I'll fold it over again. And when I open this up, how many am I going to have? 4, right? You see the 4? So with 2 folds, I have 4. Now let's make a prediction. If I fold it 3 times, how many am I going to have? 6, 8. Those are usually the most common answers I'll get. Okay, so I fold it once, twice, 3 times. 16? Is that what you said? Let's see. 12? All right, I don't know if you can see them. Got 1, 2, 3, 4, 5, 6, 7, 8. Right? 3 folds, 8 rectangles. All right, any predictions for my 4th fold? What do we got? 16. 1, 2, 3, fourth fold. We're kind of creating a little pattern here. I'm hoping that you're going to see it. 1, 2, 3, 4 across the top. 1, 2, 3, 4 down the side. 4 times 4, 16. 16 rectangles. So what's happening every time I fold it? It's doubling, right? It's multiplying by 2. So the next time I fold, I should get how many? 32. Now, any of you ever watch Mythbusters? Or used to watch Mythbusters? Okay, they actually had an episode on folding paper. And they were trying to debunk some myth that you can only fold a piece of paper so many times. And so they took this really thin sheet of paper and they put it out like in an aircraft hangar or something. And they folded and folded it and folded it and folded it. And then wound up like to get the crease nice and tight. I think they were running it over with like a steamroller. Like they went crazy with the whole idea. And there is a physical limit to how far you can go, and it's debatable. But I know that I've never got past 11 with a sheet of paper. So I'm not going to keep doing this, all right? But my question is, if we were able to continue this process, let's say we wanted to fold, let's say 9 times, how many rectangles would we have? Well, how would you figure that out? How would you do it? Tell me in words how you would do this. Number of folds, number of rectangles. Anyone have an idea of how you would do it? How many rectangles would you have for 6 folds? You would double this, right? That's what's happening every time. You're doubling, right? 8 times 2, 16. 16 times 2, 32. 32 times 2, 64, right? So I could just figure out what happens with 6, use that answer to figure out what happens for 7, use that answer to figure out what happens for 8, do that answer and figure out what happens for 9, right? So just kind of like backtrack, right? I could do that. But then if I change this to, instead of 9, changed it to like 21, then you have to go back and figure out, what happens at 6, 7, 8, 9, 10, and go all the way out to 21. That's kind of a pain, isn't there? Isn't that? It would be more efficient if we had a function that all we did is we plugged this in for the input, like x, right? And it spit out the answer for us. That would be the most efficient thing, right? So we go back to our library of functions here. Is there a function, is there a linear function that would do this? If so, what is it? Well, it'd have to be linear, maybe 2x. I don't know. Try it. You plug in 0, what do you get? 0. You don't get 1, so that doesn't work. What if you plugged in 1 here? What would you get? 2. That works, right? You plug in 2, what would you get? 4. That works, but here's where it breaks down. Plug in 3, what do you get? 6. And so you see that it's not going to work? So it's not linear. How about quadratic? Well, you could mess with that. I'm here to tell you that no linear function, no quadratic function, no polynomial function, and no rational function is going to work for this. It's not. You need a different type of function, and we call them exponential functions. That's what will model this. All right? Ember? Okay. I'm not going to have you surfing the web on your computer today either. All right? The naming of the function, exponential, this is going to have to do with exponents. And if you look back at all of these functions, linear, quadratic, polynomial, anytime we had our variable x, it was either x to the first power, here x squared, polynomial could be x to the n, and then this was a ratio of them, right? The exponents were numbers, weren't they? That's what they were here. Here with an exponential function, our exponent is actually the variable. That's the major difference. So to kind of motivate it a little bit more, I want everyone to realize that 2 is 2 to the first power, that 4 is 2 squared, 8 is 2 cubed, 16 is 2 to the fourth. Do you all agree with that? If you did, 2 times 2 times 2 times 2, 4 times, you get 16. And notice that the exponent matches up with the input, right? The 3 here matches up with this. The 2 matches up with this. The 1 matches up with this. And then, look at that. What about this one? 2 to the 0. Well, anything to the 0 power is 1. So this works. All right, so the function that would represent what's happening here should be the function where the exponent is x, and the base, we call this the base, is 2 to the x power. So with that in mind, you'll need your calculator, all right? You're going to need to be able to do powers. So please get your calculators out. And for the calculator that you're supposed to have for this class, there is that what we call a caret key. So what you're going to do is you're going to type in 2 caret, and we're doing this example right here, 9. 2 caret 9, and you should get 512. So that's how many rectangles you would have. Everyone got that? Try 2 to the 21st. Oh, okay, that's not so bad. 2097152. So if you could fold it 21 times, it would be 2,097,000, something like that, rectangles. And that's why it becomes physically impossible. Just think about this for a second. If I fold this 0 times, how thick is it? Well, 1 sheet of paper, right? If I fold it 1 time, how thick is it? 2 sheets of paper. If I fold it three times, how thick is it? 8 sheets of paper thick, right? If I fold it 4 times, it's 16 pages thick. You understand? If I fold it 21 times, how thick is it? 2 million pages thick. Have you seen a 2 million page textbook before? Have you seen a 500 page textbook? This big? Imagine a 2 million page textbook. That would be, bigger than this building probably. And this sheet of paper is only this big, right? So how are you going to create a stack of paper that's larger than this building out of this? It's impossible. All right? Okay, so that's like the idea here is that the variable is in the exponent. And this number down here we call the base. And the base does not have to be 2. For the specific example of folding a paper, the base is 2. But a general exponential function can have various bases, but they have to be a fixed number. And I'll tell you exactly what it has to be. But I wanted to point something out because some of you may notice this, some of you may not. We all have phones, right? We all use computers. And have you ever noticed that on a computer or a phone, when you're talking about like the memory, like how much space you have, hard drive space or something like that, have you ever noticed that it's usually like you buy an iPhone, it's like a 16 gig iPhone or a 32 gig iPhone? They don't have a 21 gig iPhone. Have you all ever noticed that? Yes? Do you all know why that is that way? No? It's just fun. They just like those numbers. There's actually a pretty interesting reason for it, all right? And here's the reason. Computers only know 2 things, off and on, right? That's all a computer knows. There's either an electrical signal present or there's not one. And since there's only 2 states that it understands, on or off, then we can look at everything in what we call binary, zeros and ones. And that's all a computer knows, zeros and ones. So everything being in base 2 binary is going to involve these numbers. So when you're upgrading your phone and you get a 16 gig phone or something, it's not 16 just because they like the number. It's because that's the language of the computer. All right, that's just random useless information. All right, let's get to a general definition for an exponential function. In general, an exponential function of base A is as follows. It is a function, you write f of x equals a raised to the x, where a is greater than 0 and a is not equal to 1. All exponential functions look like this. The base is that a right there. So what I'm saying is that to have an exponential function, you must have x in the exponent. The base can be any number except it has to be positive, right, greater than 0, and it cannot be 1. Now, the reason why we don't use 1 is because 1 to any power is 1. Like 1 squared is 1, 1 cubed is 1. So that's not an interesting function. We want the function to do something. So here are some specific examples. F of x equals 2 to the x. That's the one we just did with the folding paper. You could have another function, 3 to the x. You could have another function, how about this one? 1/2 to the x. These are all examples of exponential functions. Base 2, base 3, base 1/2. Is 1/2 okay to use? Well, is it bigger than 0? Sure. Is it not 1? Yeah, so that would work. So how many different exponential functions are possible? Infinitely many, right? As many numbers as you can think of, as long as they're positive and not 1. Now, 2 to the x is pretty popular, okay, because the binary stuff that I was talking about. But there's a couple of others that are really important and used a lot in mathematics, physics, chemistry. And that's some very specific bases, all right? So let me tell you what they are. 2 important exponential functions. First one, the base 10 exponential function. And this is f of x equals 10 to the x. Now, why do you think base 10 exponential functions are important? Why do you think we like those? Why do you think we use those a lot? Scientific notation, right? Isn't our number system base 10? Right? Everything is base 10. When we say base 10, what we mean is if you think of any number out there, it's going to involve one of 10 different possible digits. We have 10 digits, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. There are 10 digits. Every number is composed of those 10 digits. What if we had a number system that didn't have 10 digits, but had 6 digits, where it was only 0, 1, 2, 3, 4, 5, and that's it? That would be 6 digits, and all your numbers had to be based on those 6 digits. Then we would be really, really happy with base 6 exponential functions. So why do you think we use 10 instead of 6? I have a theory. We have 10 fingers, right? We have 10 fingers, right? When we start counting, right, we have 10 fingers. Everything's base 10 based upon that. If we had 8 fingers, we'd most likely live in a base 8 world. everything would be base 8. All right? That makes sense? So that's an important base. Another important base is one that you see a lot but don't know why it's important. This is what we call the natural base. And this one is f of x equals e raised to the x. Now that e right there is not the same e that some of your calculators use for scientific notation. I know some of you on your calculators were asking me like, hey, I got like this, 2.7e10, right? This e is not the same as this e, all right? They're totally different. So what this is, e, it's a number, all right? E is a number. Have y'all heard of pi before? The number pi, right? Everyone knows that pi is a number. It's approximately what, 3.1415 something. Keeps on going forever. Never stops, never has a pattern to it. It's just weird. We call these irrational numbers. E is another example of an irrational number. And e is approximately, well, let's see if you can find it on your calculator. Yeah, you should be able to do it on your calculator by typing in. You can do e to the first power, like if you only have an option to raise it to a power when you type it in. Did everyone find it? Where the heck is it? On this calculator, it's below the log button, log. There's another button below that's ln, and then do you see it's in the green shift? You have to hit the second button, then hit that ln button, and it'll bring up e with a little box. And just put 1 in there. 2.718 something. E to the first power is 2.718. And it keeps going. So to qualify as being an exponential function, that base must be positive. That is positive, right? And it's not 1. So that would work, right? Some crazy number. Now, why is that number so important to us? Why do we like to use it? Why do we call it the natural base? That's a hard question for me to answer without getting too detailed. But let me just say it this way. As we progressed as people, okay, as thinking organisms on this planet, we had to start to organize our ideas, and we got to a point where we were looking for a function that behaved a certain way. We're like, man, it would be really nice if there was a function that did this, 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 and this. I wonder if there is. And we searched and searched and searched, and we figured out, oh, wow, this is it. This is the one. And it only works, this function is the only one that behaves that way, and we can't explain really why it is that way, but it does. And so we call it the natural exponential function because it just kind of naturally occurs to be the one, all right? And it's used a lot in calculus. And again, I can't tell you why it's so important, but it is, all right? You just have to take it on faith. What you need to be able to do is use your calculator in here to figure out what e to different powers is, all right? All right, so now what I'd like to do is graph one of these, all right? So let's look at one of the graphs of these. And I told you before that rational functions with all those asymptotes and everything were the hardest functions to graph. Yep, these are going to be easy compared to that. And what we're going to do is we're going to use a couple of characteristics, and then we're just going to do like a t-table. And we're just going to get a couple of points and draw it, and we're done. All right. So graphs of exponential functions. Here's what they look like. Do you remember when I first introduced a parabola? You know, we said, hey, they're going to look like U's and they either open up or down, that sort of thing. Same story here, but they don't look like parabolas. They look like this. First of all, they all go through this point, 0, 1. All right? They all include that point. And then to the right, it's going to grow very rapidly. It will grow like this. And then to the left, it's going to die down, and it will actually have a horizontal asymptote out to the left-hand side, like this. This is what they look like if A is greater than 1. And in this case, we call this exponential growth. Why do you think that 0.01 is always going to be there? Think about what this function looks like, a to the x. Why is the 0.01 always there? This is going to be like that magnet thing that pulls it down. But I'm saying, why is this point always on every exponential function?
To do with the 0?
Yeah, if no matter what the base is, right? If I raise it to the 0, what's the answer? 1. And we're done, no matter what. So that point should always be there. And then to the right, it's going to go up, and to the left, it's going to approach the x-axis asymptotically, like the rational functions did. Now, if I try this and change the a little bit, see, this is what it looks like if a is bigger than 1. If I actually change it to a being between 0 and 1. So that's a number that's still positive, right? Bigger than 0, but less than 1 this time. So like a fraction, 1/2, 0.7, something like that. What happens with my graph is I still have 0, 1 there, all right? That's still there. But it's flipped, it flips that picture. It goes up on the left, and it goes down on the right like this, and it approaches the x-axis that way. What do you think we call this? Exponential, we actually use the word decay. Exponential decay. So let's do a specific example. Let's sketch something. This is what I'll be asking you to do on the test on Monday. I'm going to give you an exponential function. I'm going to ask you to graph it. So let's sketch. Let's do the rectangle problem. F of x equals 2 to the x. So first thing that you should notice when you look at this is this exponential growth or decay? It's growth, because a is 2, right? A is 2, which is greater than 1, so this is growth. So that means it's going to flatten out on the left-hand side, it's going to go up on the right-hand side. Now let's make a t-table and plug in some numbers. X, and this is 2 to the x. Now, the question will be, what numbers do I plug in, right? You can pick anything. But so that there's some consistency in our pictures, and so you're not trying to just like randomly guess, let's all do the same thing. Okay, so every time you're graphing one of these exponentials, let's do -3, -2, -1, 0, 1, 2, and 3. Let's do those 7 numbers. So we will have 7 points that we're going to graph. Everyone understand? We're all going to use these numbers every time? Okay. Now, some of these are going to be a little messy on your calculator. We need to do 2 to the -3. So make sure you type this in correctly. Use your negative key, not your minus key. What do you have? Okay, 0.125. Now, your calculator might spit out 1/8, right? It might spit out 1/8, but you can convert that to a decimal at 0.125. And just remember that when I plot this, this is going to be a point. The x is -3, the y is 0.125. So each one of these is going to represent a point on my graph, right? Anyone having any trouble getting 0.125? Jaro? Yeah? No?
Yeah, I'll get it.
Oh, no, look, I'm right here. 2 raised right here, this raised.
okay.
Raised, and then negative 3. Hit it. It's going to give you 1/8, then hit that button. There you go. All right. What about 2 to the negative 2? 1/4, 0.25. Then 0.5 for 1, right? Then you should get 1. Hey, look, 0, 1, right? That's a point I said would always be there. Then we should get 2, 4, and 8. And now at this point, we're going to draw our x and our y axes, x and f of x or y. And I want you to look at the biggest y value that comes out. What is the biggest number that we get in terms of the y values? 8. So our graph needs to make sure that it goes up high enough. So I'm gonna put this highest mark right here at 8, and then maybe 4, 2, 1. That way I can kind of mark things out. I did silence that. Okay. All right. Now left and right, I'm going what? Out to 3 and negative 3. Remember I said these don't have to be the same length. So I'm going to say this is 1, this is 2, and this is 3. This is negative 1, negative 2, and negative 3. So when you're doing this on your test on Monday, make sure you include the table, fill it out completely, all right, and then plot your points. So let me start with this first one. Negative 3.125 is going to be to the left and just barely up a little bit, right? Just barely up, so somewhere around there. At negative 2, I'm at 0.25, which is higher than this point, right? And we're just kind of ballparking it, all right? We don't have to be perfect. At negative 1, we're at 0.5, so like right here. And then we're at 1. At 1, we're at 2. At 2, we're at 4. And at 3, we're at 8. And you can pretty clearly see the exponential growth, right? Now over here, draw a dotted horizontal asymptote, and then on this side, make sure you include an arrow representing the fact that that grows. This is the function f of x equals 2 to the x. Questions? Pretty straightforward, right? Now, if I were to have gone out to 4, which I didn't, if I did, the next number would be 16, wouldn't it? Which would be, up here. And the next time would be 32. It would be double. That would be off the chart, wouldn't it? I just wanted to, just for the sake of illustrating something, can you grab me that red marker back there? You're going to have to throw it to me. Try not to hurt anybody here in the first row. All right. So thank you. I just want to compare something. F of x is x squared. That is not an exponential function, right? That's a quadratic function, right? The variables in the base, they're switched places. If I were to graph that, what would be the value at 0? So if I made a little t-table here, x squared. At 0, you'd be at 0. At 1, where would you be? 1, so they're at the same place. How about at 2? 4. So far, they look similar, right? How about at 3, where would you be? 9. You would actually be higher, wouldn't you? So you might look at this and say, hey, look, that quadratic function is growing faster, right? But just go one more spot out. Oops, that should be at 9 right there. 3 squared is 9. What about at 4? What's 4 squared? 16, right? What's 2? What would happen if we do that here? Where would it be? 16. So where would they be at the next spot, at 4? They'd both be at 16, right? So now they're the same. What about at 5? What's 5 squared? 25, but then what's 2 to the 5th? 32. 32? So now the exponential one has taken over. And if you were to graph these together, I'm going to run out of room, the exponential one would just take off. And it would just, we say blow up. It would just blow up, and the quadratic would be left way behind. So this exponential function grows very rapidly. Maybe not in the beginning, but as soon as you start getting out a little bit, man, this thing takes off. And that's why you hear it used like on the news, and you just watch TV and you'll hear people say like, oh, it's growing, crime rate is growing exponentially. They don't mean exponentially, they're just trying to get you to think fast, right? Fast growth, that's the idea here. Okay, what would happen if we change the problem? I'm going to leave that graph up. What if we change the base to 1/2 to the x? What should we get here? What type of exponential decay, right? We should get decay because the a here is 1/2. It's less than 1. It's between 0 and 1. And this should be decay. And that means our picture, when we draw it, should go like this instead, right? And we would go through and do our t-table the same way. And if you do your calculator, you're going to notice something pretty interesting. It's the same numbers except flipped over. So if you do 1/2, you have to be very careful on your calculator to use parentheses properly. So if I were on my calculator, I would type it in this way. I would go parenthesis 1 divided by 2 close parenthesis raised to the -3. That's the way I would type that in. If you do that, eight. You should get 8. Next one, if you do it properly, you should get 4. Then you should get 2, then 1, then 1/2, or 0.5, 0.25, and 0.125. So I'll leave that to you to kind of do on your own, on your calculator. Make sure you can get these. Mom, you're okay? All right. So those are all the same numbers, just like flipped over. So at -3, we're at +8. At -2, we're at +4. -1, we're at +2. Then we're still here, right? We still have 0, 1. But then we have 1/2, 1/4, an eighth, and it goes down that way. This is 1/2 to the x. And they call this exponential decay because as you move from left to right, it's decaying, it's going away exponentially. So it actually goes away very, very fast. All right, we good? You think you could graph these? All right, what if I throw you something like this? E to the x. Is that going to be growth or decay? Growth, because e is really what, 2.7 something, which is bigger than 1. So this is going to be, e is bigger than 1. This is going to be growth. And now you're going to have to use your calculator to figure out what e to the -3 is. And there should be a key on there for you to do this. You think you can handle that one on your own? I'll tell you what the first one should be, and then I'll let you get the rest on your own. E to the -3. 0.0497. Not negative, though. Shouldn't have got negative. Oh, I thought you said negative. I'm sorry. And then so on and so forth. You can finish out the table. All right? Which one do you think grows faster? 2 to the x or e to the x? E to the x. The bigger the base is, the faster it grows. All right? So if you were to graph e to the x and 2 to the x on the same graph, the e to the x is going to go up even faster than the 2 to the x does. All right, so now unfortunately in a class like this, this is all we really have time to do is just introduce exponential functions. This is what they look like. And then we move on to some applications of exponentials. All right? So you're laughing, Mom. You're happy about this?
Yes, that's why I have the rest.
Yes. Are we all clear on this concept? If I ask you to graph an exponential function on Monday, everyone's going to be okay? Yes? Okay. So now, let's do some applications.
Will it have bacteria in it?
Good. The first application I'm going to use has something to do with personal finance, all right? And this is what we call the simple interest formula. All right, so how do banks work? Banks will take your money, right, and they'll hold it for you. And they will give you some money for letting you hold it, right? So if you go open a checking account or a savings account, you go put in $1,000. At the end of the month, they're going to give you like 10 cents for that or something really ridiculously small, all right? And you say, hey, thanks for letting us hold your money. We appreciate you letting us hold your money. We're going to give you 10 cents for the month for letting us hold it. And then Sean, right, wrecks his car and he needs to replace it. So he comes into the bank and says, I'd like to borrow $10,000. And the bank says, oh, well, we just happen to have $10,000. So here you can have it, but every month you're going to have to pay us $3 for that money. They give the person who gave it to him the 10 cents and they pocket the rest, right? That's the way a bank works. They let you, they borrow one person's money to loan it to someone else for a profit. Right? That's the way a bank works. So there is a formula that we can use to figure out how much we will wind up paying if a certain interest rate is applied to our money, whether it be the person borrowing or the person who put the money in. All right? It doesn't matter. The same formula can be applied. And it's called simple interest because you can make these formulas a little more complicated, but it's kind of like the falling object on Earth with no air. Like we're just going to use a basic formula. So there's actually two of them. Formula A, Formula B. The first formula looks like this. A equals P times 1 plus R over N raised to the NT. I had a little brain fart there where I was like, wait, what was the formula again? Whoa. The other formula is A equals P times E to the RT. Now just take a quick glance at both of these formulas. Tell me, in terms of the letters, what's different? Not like the way they're arranged, just what letter, what's different? This one has an E, okay, which is that natural exponential base. It doesn't have N. This one doesn't have E, and it has an N, right? That's the major difference. And so we kind of want to know what the N represents then, right? So again, this goes back to the bank. When the bank takes your money, they determine how often they want to pay you the interest, how often they want to calculate the interest for you. N represents the number of times they do that per year. So if they're only going to look at giving you the interest once in the year, then N would be 1. If they're going to do it monthly, then N would be 12. If they're going to do it daily, then N would be 365, or whatever a bank wants to consider a year to be. All right? So here, this depends on the bank's, it's their prerogative on how they want to do that. Now, you may be thinking, well, look, I want the bank to do it more often, right? Like the more often they compute the interest, the more money I make, but it's not quite like that. If they do it one time, they do it once on all your money, all right, that you put in. If they do it twice a year, they do it 2 times, but each time they do it on half of your money. So like halfway through the year, they do it on half the money, and at the end of the year, they do it again on the half plus the interest they gave you. It's a little complicated, but the N is how many times they do it per year. But it's on a smaller piece of the money. The bigger N gets, the smaller the piece of money they do it on gets, if that makes sense. This formula is the more commonly used one, and what it does is it takes N here and it lets N become infinite. So basically they're compounding your interest, or they're calculating your interest all the time, which is a weird concept, all right? But it's not daily, it's not every second, it's infinitely many times on an infinitely small amount of money. It's weird. Take calculus and you'll understand where that comes from. So but this formula is so much easier to work with, all right? So much easier to work with. So we're gonna have to be able to do them both, all right? So I'm gonna tell you what each of the letters represents here. A is the amount in the account after T years. So that T up here is how many years you're going to leave the money in the bank. So if you're only going to leave it in there for 6 months, T would be 0.5. If you're going to leave it in there for 2 years, T would be 2. So you have to pay attention to it. It's measured in years. P is what we call the principal, but this is the amount you start with. So this would be, the $10,000 or the $1,000 that someone puts in the bank, or the $10,000 someone initially puts in, or the $10,000 that you borrow. That's your initial principal, right? What's left in here? We have A, we have P, T, time in years. T is time in years. Time in years. I'm going to run out of room down here, so I'm going to put it up here. R is your interest rate. And I want you to be extremely careful with the interest rate. When you're using the interest rate in the formula, it must be in its decimal form. Must be in decimal form. So if the interest rate is 5%, you would not plug in 5 here. You would plug in 0.05. All right? If you mess that up, everything's going to be off. And then N is the number of interest, what we call compoundings per year. And the most common N's that you're going to hear are interest is compounded yearly, which would mean N is 1, right? N is 1. Interest is compounded monthly, N is 12. Interest is compounded quarterly, 4 times a year, quarters. Interest is compounded daily. We'll use 365 in here, okay? Some banks use different numbers, right? You could do weekly. Weekly would be what? 52. Semi-annually would be twice, okay? Those are the only things I'll ever throw at you, all right? That takes care of everything in this formula, right? In this formula, everything is exactly the same. A is how much is in the account after T years. P is how much you put in. R is your interest rate. T is time in years. And then you ask, well, how many times are they compounding it? That's what I was saying. They're doing it always. They're always compounding it on an infinitesimally small amount of money, and it's don't worry about it. Do you think, just your instinct, what does your instinct tell you? Do you think that using this formula versus this formula is going to be better or worse for you? If you're putting money in the bank and you want more money back, which one do you think is better for you? Or do you think it matters? You think this can be better? It turns out that the difference between the two is usually pretty negligible. We'll see. We'll do a calculation. We'll compare the differences. All right? One of the most important numbers in the entire problem, if not the most important number in the entire problem, is R. Because that's your interest rate. When you go and you give your money to the bank, your interest rate is very small, right? Very, very small. How much money they're going to give you to borrow your money. But then they go give someone else a credit card, right? And what are the interest rates on those credit cards? 12, that's a good one. I see like 20, 25, right? I mean, it's crazy, these interest rates. It's obscene. That's how we got in so much financial trouble as, country to begin with, right? Okay, we're not going to get into that. Everybody has credit. Everyone goes spend all, just borrow it all from China.
Yeah, my parents were telling me since I actually have to get a car because I have no credit right now.
Yeah.
And so they're saying because I can't get an auto loan. Because I have no credit. Yeah, so I have to start building up credit. So
Yeah.
My mom is a big fan of Dave Ramsey. She's like, don't build credit, don't have credit.
Really? Oh no. Well, all I can say is when I was in college, you could walk around campus and they had vendors there, like from different credit card companies. I don't know if it's still like that here, but you could get like in your situation, you haven't built any credit or anything. You're just a college student with student loan debt already. Back in my day, I could get $30,000 worth of credit on credit cards. Easy. And that's why we got into such big troubles, because years and years ago, we were just giving everybody credit cards and they were living off of them. So like if you're in a situation where you're just like living off your credit cards, gas, groceries, I'll pay it all back later. That's a dangerous, I'm not here to be a financial advisor, okay? But that's a very dangerous position. I use credit cards frequently, but I only use them to take advantage of where they have these like 12 months no interest things, because then it's someone lending you money for free and the money that you have is in your pocket or in your bank and it's making money for you instead of for someone else. Yes?
I just checked the credit score on that. It said, sorry.
It said we don't we don't do negative credit.
Yeah, so like it says that like one of the categories is like the number of accounts, and it said I was poor in that part, but like I didn't get it because like wouldn't you want less accounts?
No. They want you to show that you can keep account up to date, that you can make regular payments. See, people have different opinions on personal finance. And again, this isn't a class in that, but the idea is that you have accounts that you don't want to just let them sit there and do nothing with zero balances. You actually want to charge stuff, pay it off on time, charge stuff, pay it off on time, and that shows that you are reliable and dependable, and that bumps up your credit score. But if they're just sitting there idle and doing nothing, it shows more that you get these cards and you don't do anything with them, and it's just not good to have open accounts that are just sitting there. Yeah, I mean that's why it's not helping you. Yeah. Okay, so let's do an example, and I like the example of like lottery winners because they get this huge sum of money, and let's just see like how great that situation is. All right, so let's take an example of a lotto winner. You win. No, you don't win. You're not going to win the lottery. Somebody else won the lottery. All right, I'll make it you. Will that make you happy? You win the lotto. And you did the cash out payment, all right? So you decided to, should I put like exclamation? Happy? All right, you win the lotto. How much do you want to win? Let's be realistic here. Because, Uncle Sam, if you get the cash out payment, Uncle Sam's going to take like half off the top. So what do y'all want?
Let's do 50,000 over 10 years.
No, lump sum. Lump sum. 890 million? Let's go with something I think which would be reasonable. It'd be a gray area. We wouldn't know if it's enough money to live off of for the rest of our lives or not. 2 million. 2 million? Okay. 2 million. I think we'd all be happy if we hit the $2 million lottery. But could you just like I'm quitting school. I'm doing, I mean, like, I'm set for life, okay? Let's see. For school?
Yeah, it's not even being enough
I,
for school.
2 million?
I mean,
School are you going
taxes
to?
and everything.
I don't know. You should be able to go to school and get an education for $2 million. Okay, so you got $2 million, and you're going to put it into, you would never want to do this, put it all into one bank because it's only insured for a certain amount. But this is all theoretical, okay? Let's say we put it into a bank that pays a pretty good interest rate. Anyone work in the bank industry here or know a good interest rate right now?
10%.
That's way too high.
0.7.
Yeah, it's like 1%. 3 is like the top. Let's take the top scenario, okay? Best case scenario. You invest into an account paying, we'll go 2.75%, which is high. That's another thing. Back in the day when I was in college, if you put money into a bank, you could get 3% back on that easy. In a checking account. You just throw it in a checking account and it would give you 3% back. Nowadays, no way. No way. You invest in an account paying, okay, so now let's take some different scenarios. How much would be there, be in account after 1 year if the interest is compounded monthly? And after we figure out this answer, we're going to do the same thing, and I'm not going to change anything in here except we're going to do it in a different time span. We'll do it daily or something. All right, that's the first part. Let's do that. So basically what we're going to do is we're going to put the money in there, 2 million. We're not going to touch it for a year, and we want to see how much we have at the end. So which of the two formulas are we using? The first one, right? And the reason you can tell is because they tell you how often it's compounded, right? Monthly. So I'm using this. Let's identify some things here. What's R going to be for us? 0.0275. So don't forget to convert it to a decimal. What's N going to be? 12. What's P? 2 million. And what about T? 1. 1 year. And that's it. Now it's just really a calculator problem. Now you might be asking yourself, like, why does this fall into the exponential function category? Well, this is an exponential function because it has variables up in the exponent, which is what makes it exponential. All right, here we go. I'm going to start writing it out. The amount that's going to be there will be my 2 million times 1 plus 0.0275 divided by 12 raised to the 12 times 1. Now just take your time doing this on your calculator. I recommend following your order of operations, parentheses first. Inside the parentheses you have division and addition, so do the division first. So I'm going to do 0.0275 divided by 12. And I recommend that you use as many decimals as your calculator gives you. So this is going to be 2, 1, 2, 3, 4, 5, 6, 1 plus. We do not, in other words, don't round this 2 decimal places. You got to go as far out as you can. So when I do this right here, I get 0.002291667, and then raised to the 12, because 12 times 1 is 12. When I put these two together, I get 1.002291667, right? Where? In here?
91666.
Well, yours